Good morning, chemistry students. Our next two CFAs are kind of a mixture of a couple of topics. So prior to taking them, I wanted to make certain we had a couple quick reminders and revisits on some things that we have either not had the opportunity to practice as often or may have not seen in a bit. Of course, remember that with Unit 2, we started with nomenclature skills. You will see nomenclature through the end of the semester, and you are encouraged and allowed to use the nomenclature flowcharts that are included within Google Classroom. Remember, the flowcharts, no matter which version you use, kind of guide you through either naming or writing the formula. So this is one half of the pretty color-coded one where you are going from the letters to the names. This is a similar flowchart. Same process, you're going from the letters to the names. So notice it's several yes and no questions, and you're picking the path that you need to follow. In both versions, there are examples with formulas and names, so you can kind of see how it looks at the very end. We also have the reverse of that. So when we're going from the names to the formulas, so from the words to the letters. This, again, is the other half of the colored flowchart, and its non-colored counterpart. They are really, really similar. They are not necessarily identical. The one downside to this particular flowchart is there's not examples, but this does have the examples in it, and everything's kind of sort of color-coded, so we can see our ionics, our information's all in blue. Our acids are in pink and orange, and our covalents are in yellow. So definitely please, as you are doing your practice, your quizzes, your tests, make certain you're using your periodic table, doing that Control F. You're using the correct periodic table, but in addition, you're also actually using our nomenclature flowcharts. I'm not going to spend too much time reviewing nomenclature because I do want to touch on some other items. So I do want a quick revisit for properties of compounds. This is something that until we get to Unit 3 and we're actually doing a chemical reactions lab, we don't really get to see much due to pacing and timing. We just don't have the time to do as many labs as I would like. So I do want to take a moment to revisit properties of our metallic compounds, ionic and covalent. This has to do with their types of bonds, so it does have to do with their intramolecular forces. I always want to try and say that backwards. So compare and contrasting our bonds, starting with how these bonds form. So for metallic bonds, they are literally formed by sharing the sea of electrons between metals. It can be a whole gold bar, so a pure metal, or it can be a mixture of like gold and copper. But either way, the electrons are shared amongst all the individual atoms. With an ionic bond, it's formed by transferring the electrons. The electrons are transferred from the metal to the nonmetal. Versus covalent, they share the electrons between individual elements. So the big difference between covalent and metallic is metallic, those electrons can move from one end to the other. Covalent, they're shared, but they're only shared between two elements. So the type of elements that we see in each of the bonds for metallics, pretty kind of self-explanatory. We only see metals. Metals are the only things that will make pure metallic bonds. With our ionics, we see a metal and nonmetals. Remember, you can see single nonmetals or groups of nonmetals called our polyatomics. With our covalent bonds, we see them forming between either two nonmetals or a metalloid and a nonmetal. So generally, our covalent bonds are formed with elements that are just to the right side, either on the stairs or to the right of stairs on the periodic table. My ionic has one on each side. So it has metals and nonmetals, and then my metallic ones are only metals. In terms of their strength, most metallic bonds tend to be very, very, very strong. They compete a little bit with ionic bonds depending on the compounds and the ions that are actually between them, but both of these are very strong. The fact that they have very strong bond impacts the other physical properties. Now, my covalent bonds, because we are sharing electrons and nobody really has full control over any of them in terms of our valence electrons, our covalent bonds tend to be considerably weak compared to the ionic and metallic. So metallic and ionic bonds, because they are very strong, have extremely high melting and boiling points. Some ionic compounds, they do not melt until you get to like 500, 900, 1200 degrees Celsius. Same with some of our metals. They have very, very high melting and or boiling points. Where our covalent bonds have very low melting or boiling points because it is very weak bonds. Our metals and our ionics tend to be solids at room temperatures. Specifically, ionics happen to form crystallized solids. They form crystal structures. Not that we're getting into the crystal structures for first year chem. Covalent bonds tend to be liquids or gases. If they are a solid, they're going to be very brittle or very breakable. So in terms of electrolytes, can these things conduct electricity and or heat? Metals can do both in both their solid form and their liquid form. Ionic bonds can conduct electricity if they are melted or dissolved. So I can't conduct electricity through solid ionic compounds, but if I dissolve it in water or if I melt it, we can actually use it to transfer electricity from one location to another. Versus our covalent bonds cannot conduct electricity. They are called non-electrolytes. These would be things like fat and butter. They are made up of a whole bunch of bonds that are shared and the electrons are not able to flow through the substance. In terms of their durability, breakability, metals, you're able to bend metals without actually breaking the attractions because of that sea of electrons. We can bend and reshape. That's why metals are malleable. That's why they are ductile. That's why we're able to make a lot of the things that we make with our metals. Our ionic bonds tend to be very brittle. So because if we were to knock them out of alignment, you would end up with negative ions next to negative ions, and there's going to be a very strong repulsion. Remember, ionic bonds form crystal solids, so they're kind of alternating charge. And if we damage that structure, it's going to cause it to break apart very, very easily. Covalent bonds depends on the state of matter. Again, if they're solid, they tend to be fairly brittle. If they are liquids or gases, of course, you can't break a liquid or a gas, but they're, not have a lot of structure to them in those states of matter. In terms of their other names, metallic bonds can be referred to as alloys. They are only called an alloy if it's a mixture of metals. So that gold and that copper mixture is a gold alloy. Steel, for example, is an alloy. It's a mixture of carbon and iron, if I remember correctly. Ionic bonds are also called salts. I do not just mean the salt that you put on your French fries. I mean anything that contains a metal and nonmetals. So salts such as magnesium sulfate, which is also Epsom salt, are ionic compounds. Covalent bonds are also called molecules. You've probably heard this in biology in terms of water molecules. So lastly, what do they all have in common? Because they have all these differences, but what is the one thing they have in common? Well, the one thing that all of our bonds have in common is the reason why they form. The reason they form is to achieve stability. In terms of our ionic bonds, they're transferring those electrons to achieve the octet. In terms of covalent, they're sharing electrons to achieve their octet. Everybody wants to be like the noble gases because the noble gases are the most stable. They are the kings and queens of the periodic table. So all of these bonds form to achieve stability. Some of this I touched on just a moment ago. So in terms of intermolecular and intramolecular bonds, within covalent, they are divided up into two different separate categories, and it is important to know the difference and how to recognize the difference between the two. But metallics, kind of already touched on. Ionic, already touched on with the fact that it's transferring electrons between our cations and our anions, our metals and our nonmetals. But with our covalent, we have polar covalent and nonpolar covalent. So nonpolar, think no pole. So no pole means my electrons are evenly shared. In polar covalent, think pole, like North Pole. In polar covalent, the electrons are not evenly shared. There's an uneven sharing of electrons. We can determine, based on the electronegativity difference, if a compound is going to be polar or nonpolar. Our polar covalent bonds are weaker than ionic, but they are stronger than nonpolar covalent. And the electronegativity difference that determines that the compound is polar covalent is any difference that is between 0.3 all the way up to 1.7, but not equal to them. In terms of ionic, if it happens to be a metalloid and nonmetals bonding, it could be ionic, and the way you can determine whether or not for sure it's ionic or covalent is to look at your electronegativity difference. If we have an electronegativity difference of greater than or equal to 1.7, that means that compound is going to form an ionic bond. And fluorine can do this with several of the metalloids. Most of the other nonmetals I don't believe can off the top of my head. So nonpolar again means no poles. It's still two nonmetals, but there is an even sharing of electrons. The electrons are equally spread out between the two elements. In terms of electronegativity difference, you're looking for a value that is less than or equal to 0.3. So again, we are subtracting the electronegativity values. If we get 0.3, it's nonpolar, but if we get 0.4, it's polar. If we get 1.7 electronegativity difference, it is ionic. So these are all our intramolecular bonds. Remember, intramolecular bonds are bonds between atoms. I love to use the words to help me remember, and intra has that A in it, which reminds me that it is atoms. The other things you see on the screen are the intermolecular bonds or intermolecular forces. These are attractions within substances themselves. So not between atoms, but between particles of the same thing. So picture a water molecule next to another water molecule, next to another water molecule, next to another water molecule. There are some attractions between those four molecules. So the four types of attractions that I believe we discussed in class, first one being ion dipole. This is one that's not technically in our standards, but I still like to include it because it is a very strong intermolecular force. And IMF is how I abbreviate intermolecular force. So an ion dipole only occurs between ions and polar molecules. So this would be something between like the sodium ion and water when we dissolve sodium chloride within water. That's an intermolecular attraction. It only forms between ions and polar substances. So if we don't got ions or we don't have polar substances, you cannot have an ion dipole situation. These are the strongest type of IMF, but we don't talk about them too terribly much because it does require the substance to be dissolved in something else. So these other three are the three that we talk about the most because they involve pure versions of the substances. So the next one is hydrogen bonding. Hydrogen bonding involves an hydrogen that is attached to an N, an O, or an F, but that hydrogen has some attraction to another N, O, or F that has a different hydrogen attracted to it. So we only see hydrogen bondings in compounds where we have N's, O's, or F's attached to H's. So HNOF is my really stupid way to remember it, HNOF. And that attraction is weaker than ion dipole, but of the other remaining IMFs, it is the stronger attraction. So don't judge my very bad picture, but this would be, for example, again, I'm playing with water. It would be the attraction between the O and the H, this kind of little dotted line. So it's not a real bond, but it is some attraction. That attraction is what gives water many of its physical properties. So the other H's would be attracted to other O's and other compounds. Same with this upper oxygen. It would be attracted to other H's and other O's. So dipole requires polar bonds. If you don't have polar bonds, you cannot have dipole. So it occurs between compounds that have polar bonds. Not only does it require polar bonds, but it also requires the bonds to be unsymmetrical. What this basically means is the bonds don't cancel each other out. They're not the same on all the sides. So generally, you know you have an unsymmetrical bond if that central atom has lone pairs, or in the case of group 14, if the atoms that are surrounding it are not all the same. So like if I had 1 fluorine and 3 hydrogens, we're going to have a dipole. So dipole is considerably weaker than hydrogen bonding. The neat thing is if you've got hydrogen bonding, you have dipole. Because hydrogen bonding requires polar bonds, because H and N, H and O, and H and F all form very polar bonds. So if I've got hydrogen bonding, I'm going to have dipole. It does not work the other way. So our weakest and our last intermolecular force is London dispersion forces, also called LDF. And London dispersion forces are temporarily induced dipoles. It's basically the electron cloud has been adjusted due to something else coming near it, or technically in contact with it, depending on what's going on. Any compound can technically have LDFs. They are temporary, they're induced, they don't exist long terms, but the more LDFs you have, the stronger the bond is. So it does have an impact, even though it's a weak force and it's temporary, the more we have, the greater that attraction is. So, next couple of slides we're going to look at are just some examples. Part of it's going to be identifying the IMF, which is one of the skills that we will need to have by the end of the video, as well as explaining patterns, primarily in boiling point, that we see for substances. So here I've got 3 organic compounds. Notice their names are nothing like what we've seen in class. That is because they are all organic. And we have only learned how to name ionics, covalents, binary covalents specifically, and acids. So if we look at each of these substances, notice 35 degrees Celsius, that's pretty low compared to 260 degrees Celsius as our boiling and melting point. If I look at the first 2, their masses are identical. So the size isn't a factor. The biggest difference between these 2 is the position of the H. So in the diethyl ether, my O is in the middle. Yes, that's a polar bond, but it's O attached to a C. So, and it's a balanced C. It's symmetrical because on both sides they look exactly the same. So we don't have dipole-dipole interaction. We don't have the hydrogen bonding because H isn't attached to an N, an O, or an F. What we do have is London dispersion. Yep. Polar bond. Oh, well, but still it's symmetrical. Oh, it's not symmetrical. Bad misrange. See, this is why I get for not looking at it in 3D. So yeah, those lone pairs make it unsymmetrical. I have a central molecule that has lone pairs. It is by default unsymmetrical. So we do have dipole-dipole. But what does the middle molecule have that the one on the left doesn't? It's got a hydrogen bond. So yeah, it's got London dispersion. It's got dipole-dipole. But that hydrogen bonding, that H attached to that O, is going to have a massive increase. Notice more than 3 times higher. Same letters, different order. This substance is much stronger in intermolecular forces. The intra is the same. They're all covalent bonds. But those intermolecular forces is why in butanol is much, much higher. So if I look at the last substance, it's got a slight increase in mass, but really not enough to explain almost doubling my melting and boiling point. Technically boiling point. But notice, we have an ionic bond here. I-O-N-I-C. We have an ionic bond occurring. That's what that O minus and Na plus is trying to illustrate. That is an ionic compound with, think of it as a polyatomic for lack of better words. Technically it's ionic with a organic thing, but that ionic bond makes it much, much harder to melt or boil. So it's going to have a higher, or that's the reason why it has the higher boiling point. So, this slide, I'm going to go through a couple and identify the IMF, and then the next slide, I want you to see if you can identify the IMFs. So, for now, I'm giving you what they look like, but we will see later in this particular unit, we're going to learn how to draw these nice, pretty pictures that Ms. Rains has been showing you. So you eventually learn how to draw this. But CCl4, that's what it looks like. What are the IMFs that are present in it? Well, there are no ions. So ion dipole, gone. There's no hydrogen, so there can't be hydrogen bonding. Dipole. Well, yes, carbon and chlorine, that is a polar bond, but it's symmetrical because carbon's attached to all four. So because it is a symmetrical polar bond, there's no dipole. The only thing this has is London dispersion forces. All right. Look at carbon dioxide. So this is what carbon dioxide looks like. It's kind of turned sideways so it can all fit. So carbon dioxide, notice that C has exactly the same thing on either side of it. So it's symmetrical. No dipoles. No lone pairs. Definitely no dipoles. Really and truly, all this thing has is London dispersion, LDFs. Yes, it is okay just to say LDF. I will know what you mean by that. All right, my last example doing with y'all is CH2O. That is this thing down here at the bottom. So what do we have going on? Well, it's not symmetrical. And we have definitely a polar bond. That carbon-hydrogen is quite polar. Oxygen is going to be slightly negative. Carbon's going to be slightly positive. I can't do the funky little S for the partial thing. So that means we've got dipole-dipole. We got London dispersion because everything has London dispersion. But my H is not attached to an N, an O, or an F. So we do not have hydrogen bonding. So dipole-dipole and LDF, that's all we have. So these are yours. Pause the video, give it a try. Notice I gave you the pictures with it. What are the IMFs that we have present here? Alrighty. So my first one, hopefully you were able to figure out that, yes, it has LDF. Everything has LDF. It has dipole-dipole because it is not symmetrical. That lone pair of electrons around the end makes it unsymmetrical. So it has dipole-dipole. And yes, I'm abbreviating di-di. Does it have hydrogen bonding? No hydrogens to bond, so nope. Number two, does it have hydrogen bonding? No. My H has got to be attached to an N, an O, or an F. Remember, hydrogen bonding is fun. There is no fun there. But do we have a polar bond? Yes. Silicon is going to have a partial negative charge. Hydrogen is going to be partially positive, but there's H's all the way around, so it's symmetrical. So all it's got is London dispersion forces. Looking at number three, this is not symmetrical. So not symmetrical means we're going to have dipole-dipole. Everything has LDF. Does it have hydrogen bonding? Nope. Hydrogen bonding, there is no fun. So no hydrogen bonding. Looking at number four, everybody's got LDF. This has definitely got dipole-dipole because there is no symmetry here. I got H on one side, F on the other. And it has hydrogen bonding because I got an H attached to an F, or an O, or an N. Last but definitely not least, London dispersion forces, just like all of the others. Carbon-hydrogen, remember we said that bond is nonpolar. Carbon attached to carbon, it is attached to its twin, so it's going to share the electrons easily, so that is also a nonpolar bond. So this thing is a whole bunch of nonpolarness, which means no dipole. It's also symmetrical. Notice the left half looks exactly like right half. So also no hydrogen bonding. It is just LDF. So combine this with what we've been learning about earlier in this unit. We were learning about nomenclature. So I could give you structures and ask you not only to identify the IMF, but also name the compound. That means you're going to have to be able to turn that picture into something you're used to seeing. You're going to have to turn those letters and lines into a formula. So if I look at my first one here, I got O's, H's, and P. Well, most metallic element is written first. O is further on the left, so I'm going to write it first. I got 3 O's, so H3. Next on my periodic table I hit is P, so P would come next. I only got 1 P, and then I got O4. Well, now that I have it in this format, I can easily see that this thing is an acid. And since I know it's an acid, I know that it's an oxyacid. So using my real periodic table, I can see that PO4 is phosphate. So this thing is phos, technically 4-ic acid. My 8s turn into ics, my ites turn into us's. When you're a senior, you don't want to get senioritis. If you ate something bad, you're going to say ic. Now, if you had written phosphic acid, yes, I will accept it. But for some reason, English being the way it is, we say phosphoric. I don't know. Don't care. I take both. Second one, I got just Mg's. This is just magnesium. It is a metallic bond. And it is literally just solid magnesium. So that's its name. There's no nomenclature for metallic bonds. My next thing, I got B's and F's. B is further to the left on the periodic table, therefore it is more metallic. So BF3. All right, well now I got my compound. Boron. That's a metalloid. Metalloids form covalent bonds most of the time. So we're going with most of the time. This is probably going to be covalent. So this thing's name's going to have prefixes. B-O-R-O-N, boron, tri, F-L-U-O-R-I-D-E, trifluoride. All right, this one, yes, I'm showing you Bohr's model. I'm showing you Bohr's model, and I'm trying to show you how these electrons are transferring. Remember, the transferring of electron is an ionic bond. What is this thing's name? Well, turn the letters into a formula. I can see now it's CaCl2. So its name, calcium chloride. All right, bottom left corner, H is further to the left, so H2O. Guys and gals, this is water. It is always and forever going to be water. That's it. Nothing fancy. Yes, it's covalent, but it's still water. Br and F. Bromine is further down in the group, therefore it is more metallic than fluorine. So bromine would go first, fluorine would go second, BrF5. Both of these are nonmetals, so this is covalent, which means its name's going to have prefixes. So bromine, remember we don't use mono on the first element. That's the rule. 5, mono, di, tri, penta, hexa. 5 is hexa. So hexafluoride. 5 is not hexa. 6 is hexa. Mono, di, tri, tetra, penta. Bad, Miss Rains. Penta. Pentafluoride. F-L-U-O-R-I-D-E. Yes, that penmanship is awful. Guys and gals, remember you can use your nomenclature flowchart. You can have your covalent prefixes written down on your periodic table. You are allowed to use notes on your practice. Use them. Take them. They are yours. But Got to know those prefixes. So, since I goofed it up the first time, mono, di, tri, tetra, penta, hexa 6. Oops, I'm out of the camera. 6. Hepta 7, 8. Octa 9. Nona 10 is deca. All right. Last but not least, this one didn't use Bohr's model. I used the Lewis dot-ish structure, and I say ish because yes, we used X's to indicate that it lost electrons and trying to show where the electrons were lost from the aluminum and gained to the oxygen. But either way, we can see we got ALs and Os. Well, aluminum is further left than O, so I got 2 ALs, 3 Os. This thing is aluminum oxide. So, last but not least, I did also specify if it was a covalent or acid to identify the IMF. So I'm going to go through my covalents and acids. All right, so my acid here, I got hydrogen bonding. Well, it's not symmetrical. We got hydrogen bonding going on, so you got dipole-dipole. And everybody's got LDF. So, looking at my covalent, boron trifluoride, everybody's got LDF. Boron does not have a lone pair. This is symmetrical, so there is no dipole-dipole. Water, we've done to death. Hopefully by now you know that it has all 3 of the major ones. Hydrogen bonding, dipole-dipole, and London dispersion forces. My last covalent, BRF5. Ooh, we have a lone pair on that bromine. That means this is not symmetrical. So yes, we have dipole-dipole. We have LDF because everybody has LDF. But there are no H's, so can't even consider it hydrogen bonding. So no hydrogen bonds. All right, couple quick check questions before I show you the summary slides of your properties of ionic covalent compounds and IMFs, inter and intramolecular forces. So, which of these compounds is more likely to have hydrogen bonding? Explain its physical properties. So basically, which one of these things has hydrogen bonding? Well, okay. Realizing that yes, at this point in time, you don't know how to draw these pictures, we can rule some things out. There's no hydrogen. There's no way hydrogen can attach to an N, an O, or an F. There's no hydrogen attached to an N or an O and F. There's no hydrogen. So this one, could it have hydrogen bonding? Well, technically no. Right now you don't know why, and that's okay. So the hydrogen is not attached to the fluorine. We will see how Miss Raines knows how to draw this later and how I knew that the F had to attach to the C. But that's what it looks like. So none of those have hydrogen bonding. So be careful when you look at just the letters. You sometimes will need to draw the picture and figure out, what is its Lewis structure in order to know for sure that you actually have hydrogen bonding occurring. Alrighty, so this one, what's the state of matter? Which one of these things is more likely to be a solid? One's a liquid, the third's a gas. Easiest way, let's figure out the kind of bonds. C and O, that's covalent. Zinc, ooh, that's ionic. That's going to be my solid. Because I only got one solid, so that's got to be my solid. I got a whole bunch of C's and O, C's and H's, with an OH here at the end. Okay, well, this is covalent because it's a whole bunch of nonmetals. But between carbon dioxide and that other thing, who's going to have more stronger IMFs? So they're both covalent. This one on the right. Because it's got OH. It is literally showing you that it's got hydrogen bonding. If it's got hydrogen bonding, it's also got dipole-dipole. Carbon dioxide, we saw earlier, it is literally only LDF. So it's going to have to be the gas. The other thing has to be the liquid. And those are all the forces that are involved in it. I think I went through all of them already. All right, last but not least, might give you an image and ask you to tell me what's the IMF present. It'll be images similar to what we have already seen. Notice this is specifying the pink dotted lines. That is not a covalent bond. That is trying to illustrate an IMF, specifically a hydrogen bond. So if I had something else there, maybe instead of an H, I had F's. It's not a hydrogen bond. It's trying to illustrate a dipole-dipole. But it's still an IMF because it's a dotted line. It is a temporary, not a temporary, bad Miss Rains. It is an attraction between molecules, not things between elements. It's not a bond. So I know this is a lot on one slide. Highly encourage you print it out, put it in your notes. This is not only our IMFs, so this is new stuff today is in purple, but this is also our intramolecular forces that we've seen earlier in the unit. So everything, all intra stuff at a glance. From strongest to weakest. And yes, again, sometimes there's a little bit of flip-flop with the ionic and metallic. Extra stuff goes into play that is beyond the scope of this course.